What's up, guys? This is me, Sir Ernest, and today we're going to have an example related to energies, mechanical energy of particles under the influence of a central force field. So our problem reads, a particle of unit mass m is projected with a velocity v0 at right angles to the radius vector at a distance a from the origin of the center of the attractive force, given by this equation. So we notice that the equation of the force is both follows an inverse cube power law and an inverse to the fifth power law. So here we assume that, or we set that the square of the initial velocity is equal to 9k over 2a squared, where k is a constant and a is the distance of your particle initially from the origin. Okay, so in this video we're going to focus ourselves in this problem. Find the polar equation of the resulting orbit. Okay, so let's first try to draw our problem. So as mentioned here, for example, this is your x and y coordinate axis. So initially, the particle is at a away from the origin. So if this is your origin, this is your particle. Let's say the particle has mass m, and it's already mentioned that it has a unit mass. So that means m is equal to 1. Okay, so initially the particle is projected with the velocity v0 at right angles with the radius vector at the distance a. So that means this is your distance a and this is your initial position vector, and the velocity is perpendicular to this r. So it's possible that at a later time t, this particle moves at another position. So let's say we don't know yet the orbit. So let's say arbitrarily at a later time t, it's here, and the particle move in this direction. This is your mass. So that means at a later time t, the particle has this position vector. Okay. So here we note that the initial speed is just the square root of this. So that's 3 over a times the square root of k over 2. Okay, and we take note that the total energy is E equals T plus U, or simply 1/2 mv squared plus U, which is a function of r. So we know that the energy U, or the potential energy U, is related to your force function. So we can actually calculate or determine the potential energy from the force function. So we know that the force function is equal to negative derivative of U with respect to r. Okay, and this is equal to this. So this is negative k times 4 over r cubed plus a squared over r to the 5th. So therefore, we can integrate du equals negative integral of the force function. So this is k 4 over r cubed plus a squared over r to the 5th dr. Okay, so here we're going to select our integration limits. Because as you will notice that as the particle goes, as the point goes farther from your origin, the force decreases. So therefore, the potential energy will be insignificant there. So that means at r to infinity, our potential energy is 0. And at a later point r, your potential energy has value u as a function of r. Okay, so again, u at r equal to infinity, we set that to 0. So therefore, the potential energy is now equal to negative k times 2 over r squared plus a squared over 4 r to the 4th. Okay. On the other hand, the kinetic energy, so here we note that the kinetic energy at time equal to 0, which is equal to 1/2 m v naught squared, which is equal to 9k over 4 a squared. Okay, again, m is equal to 1, v naught squared is 9k over 2a squared, and then times 1/2, so we end up with this equation. Okay, so let's call this T naught. So from there, we can also define u at time equal to 0. Let's call that u naught. Okay, so here our r naught is equal to a. So therefore, this is equal to negative k times 2 over a squared plus a squared over 4a to the 4th. So that's 1 over 4 a squared. So that's 2 plus 1/4. So that's 2 plus 1/4. So that's 9 over 4 negative k 9 over 4 a squared. So what do you notice? So you notice that this is actually equal to negative t. So from here, therefore, we can now safely assume that, or we can safely state that the total energy, which is a constant, is equal to 0 at any given point in time. Amazing, right? So now, let's compute for the equation of polar equation of motion of your particle. So we know that the total energy is 0. Okay. Also, if you want to calculate the angular momentum, the magnitude of the angular momentum is mRV sine theta, which gives us the length, the angular momentum per unit mass to be RV sine theta. And because this is constant, we can identify the angular momentum at any point in time, and we know that that will be the same for all other paths, or for all other instances. So initially, we know that at r equal to a, the speed is v naught, which is equal to 9 3 over a times square root of k over 2. So this tells us that L is equal to a v naught, since theta is pi over 2. Again, this one. So this is theta over 2. So therefore, L is now equal to 3 times square root of k over 2. So we multiply this with a, so we'll end up with 3 times the square root of k over 2. And we know that L is equal to r squared times theta, which tells us that theta dot, this is r squared theta dot, so that means theta dot is equal to 3 over r squared times k over 2 to 1/2. So we know that r dot, on the other hand, which is the time derivative of r with respect to time, is equal to derivative of r with respect to theta times derivative of theta with respect to time, or simply derivative of r with respect to theta times theta dot. Okay, so this allows us to express a general expression for the kinetic energy T, which is equal to 1/2 mv squared. We already know that v squared is equal to r dot squared plus r squared theta dot squared. So this is 1/2 m r dot squared plus r squared theta dot squared. Okay, so we know that m is equal to 1, r dot is equal to this, and r squared, theta dot squared, is equal to the square of this. So that means the kinetic energy can now be rewritten as 1/2 times derivative of theta, derivative of r with respect to theta dot, then we square this, plus r squared theta dot squared. So therefore, or this is equal to 1/2 times derivative of r with respect to theta squared plus r squared times theta dot squared. So we factor out theta dot squared, which gives us the expression 1/2 times derivative of r with respect to theta squared plus r squared times 9k over 2 r squared. So this, together with our expression for u, the general equation of your equation of energy of the orbit becomes t plus u equals this. So this is 1/2 times derivative of r with respect to theta squared plus r squared times 9k over 2r to the 4th minus k 2 over r squared plus a squared over 4 r to the 4th equals 0. Okay, so evaluating this equation, okay, you can do the algebra later. We will end up with this equation. Okay. We will end up with this equation. That's 9 over r squared times derivative of r with respect to theta squared plus 1 minus a squared over r squared, and this is equal to 0. Okay, so again, it's your task to show that this equation will yield this equation, or will be simplified with this equation. Okay, so multiplying both sides of the equation by r squared over 9, we have derivative of r with respect to theta squared plus r squared over 9 minus minus a squared over 9, and this is equal to 0. So this gives us this equation, derivative of r with respect to theta squared equals 1 over 9 times a squared minus r squared. Or, so from here, or derivative of r with respect to theta equals 1/3 times a squared minus r squared to the 1/2. Now let's solve this differential equation. Okay, so this differential equation can now be rewritten as an integral equation. This will be rewritten as integral of dr over a squared minus r squared to the 1/2 equals integral of 1/3 d theta. So here we're not yet going to apply any boundary conditions or any initial conditions. So we're just straight to solving this equation. So from this equation, so this integral is very easy, but this integral is a bit harder. So again, it's your task to do the integration yourselves, and we just skip to the final solution. The final solution to this integral would be sine inverse sine of r over a. This is equal to 1/3 theta plus c, capital C, where capital C is your integration constant. Now, let's apply initial condition. So what is the initial condition that we're going to apply? So the initial condition that we're going to apply is that when r is a, so remember that initially when r is equal to a, the angle, the polar angle is equal to 0. So applying this, we have, this is sine 1, arc sine 1, this is equal to c, which tells us that c is pi over 2. And this yields to our polar equation wherein arc sine r over a is now equal to 1/3 theta plus c. So taking the sine of both sides, so this is r equals a sine 1/3 theta, and this is 1/3 theta plus pi over 2. Or theta as a function, r as a function of theta is equal to a cosine 1/3 theta. So this is the polar equation of the resulting orbits. And what does it look like? Okay, so this equation looks something like this. Okay, so initially the particle is here at A, so it's slowly moving in this direction. Okay. Okay, so that ends our solution to problem 6.14 letter A. So in the next video, we're going to answer 6.14 letters B and C. Okay, so see you in the next video. Thank you for watching. Bye-bye.